All right, so today we're going to go ahead and move on to our next topic in the section. So far we've talked about what limits are. We talked about how do I deal with a limit if I give you a graph. And then we talked about how do I deal with a limit if I give you like an expression. And then from there, we talked about a little bit of an application talking about continuity. So basically the first four worksheets. We did also talk about the precise definition of the limit, but that one was just sort of an extra detour lecture. So today we want to talk about limits at infinity and then horizontal asymptotes. So the first thing we'll do is let's go ahead and look at this. We're actually going to jump straight into an example here. Example one, consider the graph of this given function right here. It's f of x is equal to 1 over x plus 3 plus 2, so since I changed that. So if I look at this graph, and what happens if I go as x goes to infinity, and what happens if x goes to negative infinity? So let's answer that first question. I've got a graph here, right? What's happening to my graph, the y values, if I go towards infinity, that is towards the right? What's happening with my y values? Like if I kept on drawing this graph, what do you think is gonna keep on happening? Yeah, it's gonna keep on continuing. But by the way I've drawn this, it looks like it gets really close to this line right here. You can imagine that there's a imaginary line here. This is gonna keep on going on forever and ever, but it's gonna keep on getting closer and closer to what y value am I at right here? 2. So you can imagine as x goes to infinity, or in other words, as I keep on going to the right, the y value that I'm approaching is 2. What about as x goes off to negative infinity? What y value do you think I'm heading towards? So if I look towards the left, also 2, right? Because here in my graph, it's getting closer and closer to, it looks like an imaginary line at y is equal to 2. So what we've just done here is we've actually just discussed a limit going off as x goes off to infinity. So this is me saying the limit as x goes off to infinity or negative infinity. That's me asking what's happening in my graph if I go all the way to the right or all the way to the left, if I'm talking about infinity and negative infinity respectively. So this is what we are looking at. So one thing I want to note about this problem, this is a little bit different than what we've done before. Before, we always said x was going to a number. What y value are we approaching? But now we're saying x is going off to infinity or negative infinity. So if you want to write an answer to these questions, you would say my function is going towards 2 for both of the questions, actually. All right, so we have our first example. Right now, we're still speaking very broadly. Y'all have any particular specific questions about what I've just mentioned so far? We haven't really introduced any real stuff for it yet, like definitions. All right, so let's go ahead and now look at this definition. So if I wanted this very formal definition of what we're talking about, let f be a function on some interval from a to infinity. And then remember what this little notation here means for some a and r. This notation here just means a is a real number because we have a is a. R right here means real numbers. And then this symbol means a is a real number. Then I can always write that the limit as x goes to infinity of my function f of x is some number L. So the limit is equal to L. If my function, that is my y values, get really close to that number L when x is large. So this is the formal definition. But we just applied that formal definition in that first example. All this is saying is if I keep on going towards the right, what y value am I approaching if I keep on heading right? So this is our first definition for today. I also want to clarify that whenever we have definitions, it's going to be very rare, if ever, that I'm going to be asking you, what's this exact definition word for word? These are mainly just going to be like, so that we have them for reference. So if x is heading towards infinity, that meant we were heading towards the right. So if x is going off to the towards negative infinity, does that mean I'm looking towards the left or towards the right? If I'm going to negative infinity. Yeah, so whenever I'm looking at the x values, remember I have like my Cartesian plane, the axis is my horizontal. So if x is going off to infinity, that means I'm heading off to the right. But if x is going off to negative infinity, that means I'm looking to the left, y'all's left. And that's basically what the second part of this definition is. This one, you don't really have to copy it down because it's going to be essentially the same thing, but in the other direction. This one's saying x going off to negative infinity. So again, don't get too caught up in all of these formal terminology. If we broke it down, it just means what's happening whenever we look to the far right, then to the far left. So we have our definition of a limit at infinity. So this is the part where I wanted to make a clarification from a previous lecture. What is the difference between what we've done here, a limit at infinity, versus an infinite limit? They sound very similar. Anyone remember what was an infinite limit? So we know a limit at infinity is whenever x is going to infinity. But we recall that an infinite limit is when my limit is equal to infinity. So infinite limit is when I'm equal to infinity. A limit at infinity is when x, like this right here, is going to infinity. So that's just a very small nuanced thing. Again, not a big deal, but if I ever just say an infinite limit versus a limit at infinity, those are sort of the differences that we know of. And there is some overlap between the two definitions. To infinity. So like what we have here, this is a limit at infinity because x is going to infinity. So that's what I mean whenever I say a limit at infinity. Infinite limit is whenever I am equal to infinity. So this does mean before, whenever I had the regular limits that we worked with in the previous lectures, when x was going to like 1, before we would say, all right, where is x equal to 1? Let's look at the left and the right. But here, I'm not really looking left or right because I'm just going all the way to the right or all the way to the left. Fortunately, overall, the concept is still the same. In the end, a limit is just asking what y value am I heading towards? What y value am I approaching? Under all of these fancy definitions and everything, that's the key concept of a limit. What y value am I heading towards? Or you can say, what height are we heading towards? All right, so Let's see, I'm going to give y'all some more time to copy this down. I see a couple of people copying this down. I think we have a couple of new folks that are just coming into the class. All these notes are posted onto Blackboard as worksheets. So don't worry too much about if you're missing a definition or something like that. Those are posted onto Blackboard. I think I've already posted the entire first unit. If anyone that's been in the class can confirm that y'all have access to it. Perfect. All right, so let's go to our next definition. What can I use with this infinite limit? Limit at infinity. So I'm going to give this definition. The line y is equal to L is a horizontal asymptote for a given function if the limit at infinity is equal to L. Does anyone in here remember what is an asymptote if we're in terms of graphing? So not a starting point. Any other ideas about or remember what's an asymptote? Sort of along the right idea. So I'm going to go ahead and draw an example of an asymptote. So if I want to draw an example of an asymptote, then I could, for example, see if I can draw it right here. Recall that an asymptote is a line where if I draw my graph, I get really close to that line, but I never actually cross it. So here I just have a random graph, for example. And if I want a horizontal asymptote, that means I'm lying flat. Let's say I have a flat line. I'm going to try to make this into a horizontal asymptote. So I'm actually going to use the graph that we had earlier. So this is my graph. We can see on this horizontal line, my actual graph, it gets really close to this horizontal line, but they don't ever actually touch each other. So an asymptote is a line that my graph gets really close to, but doesn't actually touch. So for example, here, it looks like this is going up and up further and further, but it never actually crosses this line. If I extended this, it might look something like this, where it gets really close, but it's never going to go past that line. So this horizontal line that I have here is a horizontal asymptote. And actually, we find the horizontal asymptote by finding the limit at infinity. In other words, if I gave you whatever this function was, you would take the limit at infinity and figure out what that number is. Whatever that number is, that's your horizontal asymptote. And we're going to do a lot of examples. Right now, we're just talking very generally. We haven't had any concrete examples to work with yet. All right, so this is our horizontal asymptote. Now let's actually get into dealing with examples and calculations. What can we do with it? So I have example 2. I've got parts A, B, and C here. They're all limits at infinity or negative infinity. I want to figure out what are these 3 limits. And I'm going to do some, I'm going to show some expressions that are technically not very formal, but they're going to help us decide like what the final answer is actually going to be. give y'all a second to go ahead and copy down the instructions if you want. All right, so let's go ahead and look at part A of this problem. I want to evaluate the limit as x goes off to infinity of 4x to the 16th power. So before, whenever I had like x going to 1, what was the first thing we usually did to try to evaluate a limit? We try to plug it in, right? If I can plug it in and I get a nice answer, then there's no problem. Everything's great. So that's exactly what we're going to try to do here. And it's going to be, here's what I mean by informal language. I'm going to say I quote unquote plug in infinity. Technically, I can't really do that because infinity is not really a number. But for the sake of keeping the same concept, we're going to say we're plugging in infinity. So if I plug in infinity here, then I would get 4 times, well, infinity to the 16th power. Again, this is not formal language, but it helps us figure out what's going on. So what do you think happens whenever I do infinity to the 16th power? Well, if I take a huge number and I take it to the 16th power, it just becomes an even huger number. So if I take infinity, multiply it by itself 16 times, that's just a bigger infinity. So breaking this down, I can say that this is still 4 times infinity, for example. What do you think happens whenever I multiply this infinity by 4? It's just an even bigger infinity. All right, so I tried plugging it in and I get infinity, positive infinity in particular. So as it turns out, the answer will be infinity. So this was using it in a very informal way. Now I'm going to very briefly talk about why is this true. So if I want to be a little bit more formal, remember, this is the limit as x goes to infinity, meaning I want my x to be keep on getting larger and larger each time. Well, if I keep on plugging in larger and larger numbers into this function, 4x to the 16th power, then again, we're just going to get an even larger number each time. In other words, I'm not approaching a single number. I'm just growing larger and larger each time. So this is where we say my limit is equal to infinity. Now let's go ahead and look at part B. We're pretty much going to use the same concept as what I did here. I'm going to see very directly what happens whenever I try to plug in negative infinity. So if I try to do this, quote unquote, plug in infinity, again, not very formal of me to say that, we have -5 times negative infinity to the 23rd power. So we're going to deal with this exponent first. What do you think happens whenever I take negative infinity to the 23rd power? Yeah, so first off, we know it's still going to be very large, some type of infinity. But in particular, if I take a negative number to an odd power, it's still negative. So in other words, what I have here, I have -5 times a negative infinity. Because again, a negative to an odd power is still negative. All right, so what do you think I'm going to write next in the next line? What is this going to be equal to? Positive infinity. Because, well, negative times negative, definitely a positive. 5 times infinity, I just get a larger infinity. So for part B, my answer is also infinity. So far it looks like if I take the limit as x goes to infinity, we usually get infinity or negative infinity a lot. And we're going to see that that does, in fact, happen for a lot of cases. Let's see. The reason I gave this is that right here, this is the limit as x goes to negative infinity. A lot of people make a mistake and say, oh, well, this is negative infinity, so my answer should be negative infinity. But that's not necessarily true. We saw that this is negative infinity, while our answer was positive infinity. In other words, long story short, be careful about, is it positive or is it negative? Any questions about part B of this example? Now let's look at part C. Part C looks a little bit different. We have the limit as x goes off to negative infinity of negative 12x to the negative third power. So what looks a little bit different about part C compared to parts A and B? Yeah, if I look at that power, the exponent, it's negative this time. So this is where it could make a big change in my final answer. So let's look at 12x to the negative third power. So let me write 12x, get negative 12x to the negative third. So first off, does anyone remember, what does it mean whenever you have a negative exponent? Yeah, that whenever I have a negative exponent, that's the same thing as me writing, in this case, negative 12 over x cubed. In other words, it looks like I can flip it to the bottom and make the power positive. So this is a very key part that I'm mentioning. That negative exponent is going to change a lot of stuff. Whenever I have a negative exponent, I can push it to the bottom and then make the power positive. So that was x to the negative 3. If I move that to the bottom, it becomes x to the positive 3. So that's clear. All right, so now we're going to go ahead and try to, quote unquote, plug in negative infinity. So if I try to do the limit, part C, I get negative 12 over negative infinity cubed. Again, very informal about this. So what do you think happens whenever I do negative infinity cubed? Does it become a positive or a negative infinity? Negative, just again, negative cubed is still negative. So I get negative 12 over negative infinity. But what's going to happen here, though? What do you think happens whenever I put negative 12 over a huge negative number? Like, let's say negative 12 over negative 10 million. What do you think is going to pop up? Yeah, it's going to be positive, and it's a tiny number. So if you put negative 12 over negative 10 million in your calculator, it's going to pop out 0.00000012, for example, however many zeros. What do you think is going to happen if I plugged in, let's say, 10 billion in for x in there? Or just more zeros, right? So what do you think that this limit is going to end up equaling based off what I just said? Zero. Because if I plug in like a million, a billion, 10 billion, and you're just adding more and more zeros on there. So we're getting closer and closer to zero. So you can imagine if I do 1/10, 1 over 100, 1 over 1,000, 1 over 10,000, you're getting closer and closer to zero in the long run. So I gave this example to show you that in particular, when you have a negative exponent, we do have to be extra careful. Or if I want to be more broad, whenever I have an x in my denominator, the bottom, things can change around like that. So we've just gone ahead and completed parts A, B, and C. What we had infinity, infinity, and then 0. If I wanted to, I could put this into my graphing calculator, negative 12x to the negative 3. You're going to see as I go towards the left, you're going to get really close to 0. It's probably going to look something very close to what I have here, maybe shift it down. Like instead of this, it'll probably look like this if you graph it, where it gets really close to 0 when you go left. All right, so this was our example 2. Now I'm going to go ahead and just generalize what we just said. These are a couple of theorems. Again, don't get too caught up in this notation that's going to show up on the board. Suppose I have, what I have here is a polynomial. I think we talked about this last time. What's a polynomial, more or less? Yeah, so I heard a lot of things that were correct pieces in there. So remember a polynomial, for example, we have easy polynomials, x squared plus 1. Give me an example of something that was not a polynomial. To the 25 power? Oh, 0.5 power. Yeah, so our rules for a polynomial was that I just have a line of x's to some positive whole number of powers. So like whenever I had like 3x squared plus 2, I did not want any negative powers like what we had here. And I didn't want any fraction powers. And I didn't want to divide by x. That was more or less our idea of a polynomial. And polynomials are the ones that y'all are familiar with, even though y'all probably didn't call it a polynomial. Whenever you had a quadratic equation, a linear equation, when you had x to the 1 or x squared, or even x cubed, those were all polynomials. So if you ever have a polynomial, then the first rule is that the limit as x goes to infinity or negative infinity, it doesn't really matter, of x to the n power is always infinity when n is even. So if you have x to an even power, then you know your limit of x to n is infinity. And this happens regardless on if down here it's x going to infinity or negative infinity. Someone very quickly tell me why is this true no matter what when n is even? Yeah, so if I look at this, what regardless on if I'm negative or positive infinity, what happens whenever I take any number to an even power? Yeah, if I take any real number, take it to like an even power, like I square it, then it's going to be positive one way or another. So this is the idea right here for part A. We know that by parity, positive times positive is always going to be positive, negative times negative, positive as well. What do you think happens whenever we have an odd power? What happens whenever n is even? Like if I had x cubed, what do you think happens if I was trying to take that limit? So if I had something like x cubed, right? We can try to plug in infinity or negative infinity. If I take an infinity to a third power, for example, that's just a bigger infinity, right? But depending on if I go to negative infinity or positive infinity, my final answer could be either positive or negative. In other words, if I take a negative number and cube it, is that positive or negative? Negative. What happens if I take a positive number and then I cube it? Positive. So for my second rule is that if I have an odd power and I'm doing positive infinity, then I stay positive because a positive cubed, for example, is still positive. But then if I take x going to negative infinity, well, if I take a negative number cubed, that's still going to be negative. So this is part B of my theorem. In other words, it depends on what we're looking at. The last rule that I have is, what do you think happens whenever the power is negative, based off what we saw in that example? Yeah, when the power is negative, like here, x to the negative n power, I don't care if it's positive or negative infinity, it's actually going to end up being, the limit is going to end up being 0. So these are just the generalized versions of what y'all just did in those first 3 examples. All right, so this is parts A, B, and C. And there is a part D that I'll show in a minute, but really it's just derived from as a direct result of parts A, B, and C. Really part A and C, B. So up there, I've got a polynomial. All those ends are positive. What do you think happens whenever I take the limit as n goes off to infinity or negative infinity of a polynomial like that? First off, do you think I would get 0 if I took the limit of that? Yeah, we would not get 0. And here's why. If I take the limit of this whole thing, remember, if I take the limit of a whole thing, I can just take the limit of each individual part. If this n is positive and I take the limit, that's going to be infinity, or maybe negative infinity. This right here, this is going to be infinity or negative infinity, so on and so on. So all of these are going to be some type of infinity, for example. And as it turns out, whenever I take the limit of a polynomial, something that's a long line of x's, your answer is going to be either infinity or negative infinity, depending on the highest power. Again, we're talking very theoretical here. We're going to do some examples so that we can have these a little bit more concrete. But the long story short, for a polynomial, if you have a long line of adding, subtracting, we really only care about the biggest term. So we have our theorem here. And this is what I actually mentioned, I believe, on like day 1 or day 2. These are going to be the examples that you're going to find out that we're just going to do very quickly within 10 seconds for each one, once we start getting used to it. All right, so let's go ahead and look at this example 3. And as I said, we're going to work through these very quickly, as you'll see. Evaluate the following limits if it is possible. So we have 3 different limits. They look very big, long, complicated functions. For part A, I've got the limit as x goes off to negative infinity of 6x to the 11th power minus x plus 3. So first off, is that a polynomial I see? It's a polynomial. All the powers of x are positive. I'm not dividing by x. And they're all whole number exponents. So it's a polynomial. And the great thing about taking the limit as x goes to infinity or negative infinity of a polynomial is that, as it turns out, we really only care about the biggest term, 6x to the 11th power. In other words, this part A, really we can just say that this is equal to the limit as x goes off to, I think it's negative infinity, of 6x to the 11th power. So let's take a moment there. Why am I able to basically just ignore the rest of this polynomial? Why do I not even care about minus x plus 3? It is going to go off to infinity. But in particular, if I compare 6x to the 11th power, negative x and 3, which one is giving me a much bigger infinity in the long run? 6x to the 11th, right? If I have a huge number, plus 3, that's not really going to change much. That's just a small, tiny bit. Same thing for this. Even though it does go off to infinity, it's a much smaller infinity. In other words, the way I'll word it is that the 6x to the 11th power, it sort of dominates the entire behavior of this graph. All right, so someone tell me, what is this limit going to be equal to? What do you think it is going to be equal to? So if I look at this, I think I would agree that's going to be what y'all said, negative infinity. Because, well, negative number to an odd power, negative. Negative times a positive 6, negative. We could have also said, based off that theorem we had earlier, x being to an odd power, we know that this is going to be negative infinity times a positive 6, still negative. So we're done with that one. So again, notice that I did very little calculations. The most I did was what's a negative to 11th power times a positive. All right, so that's part A. What about part B? We have the limit as x goes off to infinity of 11 plus 5x cubed. So I'll start us off here, and then I'll actually have y'all finish this problem. Remember one of our first limit laws. The limit of a sum is the sum of the limits. In other words, if I'm adding stuff together, I can just take the limit of each one individually. In other words, I can write this as the limit as x goes off to infinity of 11 plus the limit as x goes off to infinity of 5 over x cubed. Remember, I'm able to split up my limits if I want. Now I claim that y'all know how to evaluate those two limits separately. What's the limit of the first one on the left? What was that? 11. Remember, limit of a constant, if it's a plain number, no x's, then there's nothing for me to even plug in. That's 11. Plus, what about the limit of the other one? 0. Because if you want, you can write that as 5x to the negative 3 power. Or you can say that infinity is on the bottom. So we have 11 plus 0, which is 11. And we're not going to actually worry about this part C because I don't want to include this particular square root example. So don't worry about this part C. It is doable, but then just for the sake of time, we're not going to specifically talk about that one. All right, so we have these technically two examples that we've covered here. Any questions about what we've talked about so far? So the idea about this being necessary is that whenever we talk about applications and stuff, we can talk about something that keeps on growing, for example. This allows us to sort of say, all right, if I keep on, this is a random application. If I was looking at a business that keeps on growing, is there sort of a ceiling that we can look at? So for example, if I was looking at a business model that matched here, the 11 plus 5x cubed, this will tell you in the long run, it's not going to be worth it. You're going to end up with zero, no matter how much money you put into it. Again, I'm being very broad about this. But then for the top one, part A, if I continue to put money on this, if it matches this model, then it should keep on making money for us, for example. So this, in other words, saying what's the long-term behavior of this action or something that we're looking at, rather than just looking what's 20 ahead. We can look all the way over towards infinity. What happens if this kept on going on forever? So that's just a very quick idea of how we might look at it. Right now, for this first unit, it's going to feel really weird because we're not really going to do much on application. It's going to be heavy on theory and limits. Whenever we start getting into the second or third unit, we're going to start doing real applications. Like we'll start talking about velocity, acceleration, profit margins, and stuff like that. All right, so let's see. I'm actually going to go ahead and stop today's lecture right here at example 3, because I don't want to get too far into this other idea. All right, so that's all for today. Remember that there is a homework that's due on Sunday if y'all are part of the new group that just came in, because I think there's a couple. Send me an email. I can get you a 1-week extension, for example. That way you're not just blindsided by a homework assignment. Oh, it should be an unlimited number of attempts. So basically, if you get it wrong, you'll click submit, and it should say which ones are right, which ones are wrong. And then there should be an option that says like retry. If it's not doing that, send me an email because it should be definitely giving y'all unlimited number of chances. There's no penalty for doing a lot of attempts. It's not like one of those things like, oh, you got it wrong one time, minus 10%. You can keep on doing it until you get 100, technically.